Today I'm going to be talking about how we can use machine learning and AI to cure the world, which is a pretty broad and big and bold mission, and I hope I can convince you that we're currently in the right place to actually do it. So let's talk about medicine and what is some of the issues that are going on with medicine. And I could probably fill up my whole 30 minutes talking about this, right? But I'm just going to point to a few issues that I think are really relevant here. So doctors have roughly, and by design in the system, 15 minutes to take all the information and everything they can gather from a patient in diagnose and recommend a treatment, right? So here you can see some of the stats of like what is the average time that doctors spend with patients. But in most institutions, they'll actually tell you you need to spend 15 minutes, and if you spend more, you're going to be penalized. So it's really by design. Now, if you think about it, when I say information about a patient, there's a lot of stuff going on, right? What you need to gather is things like the patient's history, and sure, it might be written somewhere, but you have to read it and you have to recall everything else. There's the patient symptoms. What is the patient telling you? There's also medical knowledge, right? Now you need to gather everything that you probably learned in school and you forgot, or maybe some of it you don't, the latest research. You need to apply it to a different demographic. Who are you talking to? Is it an elderly person? Is it a young adult? And then use all of that to make a decision. So what makes it even worse, and that's the harder part of the equation, is that data is growing over time, and complexity is also growing over time. And we want better and more healthcare, and we still have those 15 minutes, right? So it's really, really hard for doctors to actually manually recommend what's good for you. Taking a step back and sort of like trying to understand, trying to understand like what is medical diagnosis? How do we define it? So there's a lot of classical definitions. I picked this one from Dr. Randy Miller, who's actually an advisor to our company. And his definition is diagnosis is the mapping from patient's data, which includes what I said before, history, examination, lab, to a possible condition. And it depends on a number of things, right? It depends on the ability to evoke history, to surface findings and symptoms, which need to be surfaced because maybe even the patient doesn't know how to describe, and generate hypotheses as you're doing that and refining the hypothesis over time to come to a decision at the end. And to make things even more complicated, you need to do that in a compassionate and cost-effective manner, right? So it's a really hard problem to solve. So it's not a surprise that when you put all that together and you look at the numbers of how healthcare is going on today, you figure out that it's pretty much a disaster, right? There's a lot of inefficiencies in the system. There's like up to 400,000 deaths, depending on the statistics you look at, that are due to medical errors, and about 4 million serious health issues. For comparison's purpose, there's 500,000 deaths from cancer or 4,000 from vehicle accidents. So it's a really, really important problem. And almost half of those events, according to some studies, can be preventable. So definitely, it seems we have sort of an imperative to do something about it and to try to use our best technology to solve the problem. So how can we improve medical care? Well, doing what we know how to do best. We can automate processes through AI and machine learning. We can make use of data, be it big or small. More and better personalization, because the more we know about you, the more we can make a better decision about what's good for you. And then improving user experience, right? Because we also want to do that in a way that you come back and you want to sort of like be a happy user of the healthcare service. So what I'm going to do in the next slides is walk you through sort of like how does this ideal sort of like AI medical system look? And there's a few boxes behind the scenes that I'm going to be describing. And how can we put all that together in order to tackle this problem of medical diagnosis and do it in a way that directly impacts the lives of the millions of healthcare customers, the patients themselves? So I'll start by talking a little bit about medical decision support and knowledge bases and what is that? And if anybody in the audience heard or read about medical decision support systems? Hands up. Maybe 10 people. It's a field that's been going on for over 50 years. So it's an old sort of like, it's a known field, and there's a lot of people that have worked on. The idea here is we have a ton of medical research that has been going on for years. We have doctors, some of which are really good, and how can we actually put that together and synthesize into some form of knowledge base or medical decision system that then we can use as an input to our AI machine learning system. So just to give you an example, Internist 1, which was later named QMR and later BDDX, is a system that started in 1971, and it was led by Jack Myers at that point. It was later led by Randy Miller, and it's considered one of the best clinical Jack Myers was considered one of the best clinical diagnostic experts in the country. He had a long slew of sort of like different titles, and he drove that system and the design of that system for many years. Now, the process of encoding a single disease into the system takes about 2 to 4 weeks of a medical expert, and they need to read an average of 50 to 250 publications on that disease just to encode it. And what they basically do is read all of that, synthesize it, and encode it in a kind of a Bayesian network where they're manually sort of like inferring the probabilities, and that's sort of like the knowledge base. And that's really interesting, and because it's been going on for such a long time, it's a really interesting sort of like source of data that you can sort of input into your system. I don't know how well you can see this. There's a lot of numbers here, but this is an example of alcoholic hepatitis, and you have different symptoms, and for each symptom, you have the evoking strength, and you have the frequency. The evoking strength basically means how specific is a symptom to that particular disease. So, for example, you have sex male or sex female, which has a 0 because it's not very specific. I mean, there's a lot of males and females in the world, and that doesn't tell you much about the disease. And the frequency is the other way around. So it's basically telling you how frequent is that symptom happening in the context of that disease. So out of 100 or out of 100 patients, how many patients actually have that particular symptom? And when I say symptom, sorry, I should be using the word finding, which is a more general word. Actually, male, female is a finding. It's not a symptom, right? So all of that goes into that system. Now, I think it should be obvious that you can do similar things now, but using machine learning and AI. And obviously, has been a growing field of sort of like people in research that do use data to try to infer a similar thing to the manually encoded knowledge base that I just described. So the early decision support systems were using Bayesian networks, as I mentioned, some of which were manual encoding, some of which were some people tried to derive from data. And then lately, there's a lot of interest in actually using deep learning and neural nets. This is an example of 2 papers from the last year. The first one, Dr. AI, is the second half of 2016, and Deep Patient, same thing, or maybe beginning of 2017. In the case of Dr. AI, they're using recurrent neural nets to basically model the temporal effect of like how patients evolve over time. In Deep Patient, they're actually using an unsupervised approach using stacked autoencoders, 3 layers of autoencoders to learn a representation of the patients, and then they use random forest as a classifier to do the final diagnosis. So this is all very recent and very novel and very new, and it's really telling us like how the field is moving forward from sort of like the traditional AI, which is manually encode something from experts and then let it work on its own, to the machine learning derived AI, which is like feed data and let the model learn. And very related to what I was just saying, there's a number of initiatives in the past few years that instead of learning the whole diagnostic system all at once, what they try to do is learn the representation. So that's similar to the Deep Patient unsupervised aspect, where you're learning the representation of the patient and the diseases in that space of concepts. It's usually called, that's what people usually call health knowledge graphs. And there's a number of papers here. I have 2 of them, one from Stanford, the other one from MIT, where they basically learn graphs of concepts and relations between those concepts from the data itself. Okay, cool. So that's a good starting point. We have ways to represent knowledge and to infer knowledge, be it from experts or be it from the data itself. But that's not all. There's another aspect, which is the fact that medical practice is very conversational. As I said before, doing a correct diagnostic depends on your ability to extract information from the patient. And that's really sort of a natural language understanding problem. You need to start a dialogue, have questions and answers, and follow the information. So there's a lot of work to be done on the natural language aspect of medicine. Let me start by mentioning that there has been, just as I said with the expert systems, a lot of work on ontologies. So these are the three sort of like most typical ones that you'll hear about: SNOMED clinical terms, ICD-10, previously ICD-9. So this is the latest incarnation of the International Statistical Classification of Diseases. And UMLS, which UMLS tries to be or attempts to be sort of like a meta-ontology on top of those, and actually has some relation between concepts in the different ontologies. So that's a good also starting point, right? You have some structured knowledge that you can use and has been agreed upon. It's not perfect, but it's there, and it's a good starting point. Besides that, though, what you really want to do is use NLP techniques to, as I was saying, understanding what doctors and patients say, right? And it's on both sides. You need to understand what patients say, and you need to understand what doctors say. And you can even try to extract knowledge directly from medical publications, which is, again, a natural language understanding task, because you're going to have to read natural language text. So there's also a lot of recent examples of using NLP and deep neural networks and deep reinforcement learning, like the reference that I have here, on basically trying to map natural text into concepts. And when I say concepts, I'm actually referring concepts in the previous ontology. So there's a very interesting problem here of how to sort of like use an unstructured input like raw text and actually being able to map it into a structured ontology that has been agreed upon and has some meaning and has some relations between the concepts. So that's another aspect, and it's not very different from what you might have heard Google did with the Knowledge Vault, for example. Now, this is easier in the sense that it's constrained to a domain in which we can allow ourselves to have a reasonably good ontology and apply that to infer knowledge. Now, I've been talking a lot about using data to infer things, but I haven't really mentioned like where does the data come from. So for both the health graphs that I mentioned, as well as for some of these natural language understanding tasks, especially when it's about understanding concepts that the doctors say, we usually look into and tap into what's called EHR, electronic hospital records, or EMR, electronic medical records. This is how an electronic medical record looks. I know it looks very 90s or probably older than that, but that's really how it looks on the screen of a doctor that is basically asking you questions and trying to type at the same time. So that's why doctors don't look at your face anymore when you go to their visits. There's actually a very good article in the New York Times 2 weeks ago precisely about this. It's like, why aren't doctors looking at you anymore? It's because they're typing this into the EMR or EHR systems. But the interesting thing is that there is some structured and unstructured data in this EMR records. There's structure because the doctors select concept and they say, okay, this is my diagnosis, these are the symptoms. There's unstructured because there's doctor notes, so you can actually parse those doctor notes and extract concepts, as I mentioned before. So here's an example of a recent publication about extracting information from textual documents in the electronic health records. Another example, which that's kind of an interesting side note, but there was a paper published this year also about using GANs to generate artificial patient records, because that's a way to preserve privacy and anonymity, and it's also a way to sort of like basically increase your training set if you're training a model. So that's very interesting. Okay, so NLP, it's about understanding, and it's about understanding all these different things: patient understanding, doctor's notes, medical research publication, and sort of like mapping all of that into so-called language of medicine. Next, so it's not only about text, right? If you go to a medical visit, you have a rash, you're going to be talking to your doctor and say, hey, I have a rash. And the doctor's going to say, okay, can you describe it to me? No, she's going to ask you, like, can I look at it? And you're going to have vision coming into place. So there's a lot of different multimodal inputs going into making a correct diagnosis. So just to name a couple, you have sort of like pictures that can recognize skin-related diseases. You can do, and this was a pretty impactful publication from last year also about using images of the eyes to detect diabetes. You can also use speech interfaces, right? Because you can talk to the people instead of sort of like using directly NLP. Or you can also increase sort of like having a lot of different other sensor lab or lab data. It probably should be obvious to people that besides sort of like talking to your doctor, you're going to go and have to take some test, and you're going to have some blood test taken or any other test, and you're going to have to input that into the decision system. So the interesting thing is that all this input can also benefit from machine learning. So all these things, recognizing images, recognizing patterns from a heart rate, they've been advances over the last couple of years where you can use AI and machine learning to infer and extract information and represent it in a way that then you can feed back to your machine learning decision system. The last thing is personalization. As I mentioned before, one of the really key issues in making a good medical recommendation is understanding you as a patient. And it's not only about your medical history, it's about everything else. It's about your age, it's about your family history, it's about your ethnic background. All of those things come into play, and they're extremely difficult also for a doctor to sort of like put them all together, right? So how about if we build systems that are personalized? And of course, people have thought about it, and there's a lot of work on something that's called precision medicine. So precision medicine, according to the NIH, the definition is an emerging approach for this disease treatment and prevention that takes into account individual variability in genes, environment, and lifestyle for each person. So even though the term is relatively new, if you think about it, it's been around for some time, right? So if you have to have a blood transfusion, you need to get it from somebody that's compatible to your type. So there needs to be, at least at a high level, some form of personalization. And that's a very crude form of personalization. But for those of us that have worked on personalization for many years, we understand that you start with a very crude personalization, and then you dig down into sort of like more granular data and more information, and eventually you're able to recommend individual things to each person. So you can get things from the patient profile and medical history, right, and try to build a personalized model out of that. But you can also get things from all the other biological markers and lab data that I was telling you before, right? So basically, that doesn't only become an input to the current session, and it's not only about, where's your blood pressure today, it's about how has it evolved over the last month, or do you have a history of something, or what is your heart rate been for the last few months, right? So all these things sort of like can also be part of what becomes the personalized system. And how do we build personalized systems? So of course, I think every time that I've come to MLCom for the past 4 or 5 years, I've been talking about building personalized systems. So there's a lot of techniques that you can apply from all those other domains to sort of like infer this information and treat it and use it in the context of that person versus sort of like the average population. There's publications, also recent publications, that talk about concepts of health recommendation systems. So all those things come into place when you're building this sort of like machine learning medical system. And one of the interesting things to think about is what is different. So I've talked about a lot of similarities and a lot of things that basically it seems like you only need to plug in together all these things that we've been doing research on and make it work. There are a few things that you need to be aware of when building this kind of systems. One is what I'm calling now the self-driving car paradigm, because I think when I use the self-driving car metaphor, it's easier to understand. It's the cost of errors, right? It doesn't really matter if you're able to save thousands of lives a year with self-driving cars. As soon as a self-driving car kills somebody, it's going to be on the front page of every newspaper, right? So in healthcare, it's even more so. So there's a lot of statistics and data, and we can prove that we can build a system that it's better than the average doctor, but that's not enough. We need to make sure that it's better than the average doctor, and maybe even the best doctor, but at the same time minimizes fatal errors. So that's something that is really important. And yeah, you can sort of like assimilate it to a little bit of the trade-off between precision and recall, but there's more to it, right? So going to a fully automated AI machine learning-driven system, it's still a little bit far from where we are right now, but not from a purely pragmatic aspect. It's one of the reasons is this. The other one is causality. When we recommend you to watch the next movie or the next read your next article, why it's being recommended the causality, although I know my friends from Netflix will disagree because they've talked about causality also in the context of movie recommendation. It's not as important as it is in healthcare, right? In healthcare, you really want to know, you're telling me that I have this disease, why are you telling me? And correlation sometimes can be very confusing. All diseases are correlated to pain. Sure, I mean, not all, but most of them. But that's not telling you enough. You want to know in what direction does the error flow, right? Is it a cause, is it an effect, and what's causing what? And not to mention when you have comorbidities where you have sort of like different diseases and there's different causes and relations between those diseases. Also, I would argue that in this case, implicit user signals are not enough. That's why conversational systems are so important, right? It's not enough we sort of like put you through a scanner, scan your body and say, okay, this is what you have. You actually need to have a conversation to understand and extract information. That process is extremely important. And finally, there's a lot of complex interactions, as I just mentioned, between diseases, between symptoms, medications, temporal effects, what came before, what came after. It's extremely important, and that's hard to model into a system. Okay, so I've been telling you a lot about this whole space. I won't be telling you a lot about Curai. We've only been working on this for 3 months and a half or so, and we're stealth. So I hope you can infer what I've been telling you, and now, like, what are we working on? We're probably going to be coming out of stealth soon, but this is as much as I can say. I can say that we have an awesome team already, and we're up to 9 people, and we have people that come from Netflix, Quora, myself, Facebook, Google, Microsoft, Uber, Stanford. There's 2 engineers here in the audience that you can talk to also. And we're combining AI and machine learning, but also, very importantly, best practices in user experience and product design. And we think those 2 things need to go hand in hand in this kind of a product, right? If you're building something that is customer patient facing, the back end, the machine learning, the AI, the data is super important, but building something that people want to use and engage and trust is almost as important or more. We're leveraging pre-existing resources, some of which I have described in the slides previously, and also the state-of-the-art approaches that I mentioned. So putting all that together, and we're stealth. So that's all I can tell you for now, but I hope next time that I come to MLConf, I can already start showing demos and things like that. There's definitely challenges, right? There's algorithmic challenges. Combining expert systems like the one I described with some of the machine learning derived systems, it's not easy. You can start with ensembles, but it gets complicated and you need to sort of like merge different probabilities in different ways. It's interesting. It's an interesting machine learning problem. Data is also an issue. So there's some data. You can find a lot of data, but bad data. You need some quality, and you need to generate data that is better quality than the one that exists. And also the user aspect that I mentioned. And the legal aspect, which is a minor one, but it's also sort of like constrains a little bit what you can do, at least as of today. But regardless of the challenges that we have, I think the point that I try to make is it's about time that we overcome all of this, right? We've mastered the art of sort of like getting people to click to an ad, and now we need to put sort of like our best minds to sort of like solve really important problems like healthcare and medicine and lowering the barrier to entry to good quality healthcare and saving lives. I think it's a pretty important mission, and I hope that more people sort of like jump on board. So I'm listing a number of references here. They're on the website. The interesting thing to note is that most of the references that I use today, they're very recent. So they're 2016 and later. So that also gives you a sense, because I sometimes hear people say, oh, but hasn't this been done before? Like, wait, sure, people have tried to do them before, but there wasn't the technology, it wasn't the time, there wasn't the data, there were a lot of things missing. There's a lot of work, a lot of research happening as we speak on this field, and I think it's ripe for sort of like some kind of disruption. And of course, with that, I'll say that yes, we're also hiring like everyone else, and I'm looking forward to your questions later on in the coffee break. Thank you.